Okay, as I was saying, the presentation is recorded. The Q&A will not be recorded, so that everybody is aware. So just a few words about the Royal Nautical Society for those of you who are not already members or fellows. So the Royal Nautical Society is the oldest aeronautical association pretty much on the planet, because it was founded in 1866. So a few decades ahead of the first flight of the Wright brothers. Currently, it's got effectively sites and branches pretty much all over the world. Wherever there's a big aviation site, let's say, you can find a Royal Nautical Society branch. The Berlin branch, Berliner Brandenburg branch, was officially established in November last year. We had done a few lectures before, but we officially were established as a branch last year. And the chairman, Matthew Barnard, is the secretary here. Matthew will also report for Royal Nautical Society from ILA, so from the Berliner show next week, so you may see him around as well. The president is Martin Molby, who used to be chief engineer here multiple times, technical director at EPI. Right, now, this year we are quite busy in terms of lectures. As you remember, we had a lecture last month about the power gearbox with Sonia Nattigal. We'll go through a very good topic today, which is sustainable aviation fuels. Then we have an embassy event, which is restricted, so that's only for the people who have been invited. That's on the 13th of June. That's about NATO and the collaboration between armed forces, governments, and industry within NATO. And then the next lecture, which will be public, is on the 4th of July. That's going to be again a lecture here about the aircraft design certification process. Now, I'm really happy to have Sara Kreil here. Just a few words. Obviously, Sara is Canadian, yes. And she's been with Rolls-Royce
almost 18 years.
18 years already. She's chief dev engineer for Fleet, and she's until the 1st of June. But you stayed at Rolls-Royce in any case. Yeah. Yeah, you've been following very closely this topic, which is sustainability. And I think it's super important for all of us to understand where the aviation is going and why we need to do this. So I think it's a great topic. Thank you very much for coming with us, and I'll let you start.
Okay, can everybody on the phone hear me and everybody in the room? Okay. First of all, thanks a lot to everybody for showing interest in this topic. Emmanuel gave part of my introduction already, so I don't need to repeat it. So the presentation will be maybe about 60 minutes, and then hopefully we leave lots of time for good questions. Yeah, so let's go ahead. Before I get into the main content of the pack, for maybe some of the people on the phone that are not familiar about what sustainable or what SAF is. So SAF stands for Sustainable Aviation Fuel. There's a lot of misconception between the differences between other sort of non-fossil based fuels and SAF. So there's a lot of synthetic fuels or non-fossil based fuels that are made from non-sustainable material, such as coal or gas. And then there's a term that's been widely used in the past that's called biofuel. Biofuel is fuel that's generally made out of corn. That's not a SAF fuel. So the differentiator is that the feedstock that's been used to make SAF truly comes from a sustainable source. And I'll get into a lot more detail about what makes up SAF in the later part of the presentation, but just to set that as the base. If we take a big step back, so why do we bother doing all of this stuff? There was the Paris Agreement that was agreed in 2015. And that's not an aviation target, but that was an overall climate target that we need to control global warming to no more than 1.5 degrees more relative to pre-industrial times. So the year that stands for, to be honest, I haven't found an exact date, but it's around 1995. Because if we trend what the global, or what the average temperature of the ocean has been between 1995 and now, it's increased. If it continues to increase at that rate, then by 2050, a large portion of the Earth will no longer be inhabitable. So that was the target that was set by the Paris Agreement. And there are many different industries which contribute to CO2 production. So obviously like the forestry industry, agriculture, and all that kind of stuff. And the contribution of aviation in the overall perspective is relatively small. So it's about 2% of the total CO2 production, of which business aviation is also an even smaller percentage. But the reason that aviation needs to do this is that aviation produces a significant amount of other pollutants that are non-CO2, and it's considered to be the fastest growing polluting industry over the next period of time. So that's why we have to do this, and why we want to do this. Aviation's contribution to global warming is not just a CO2 effect, it's also a non-CO2 effect. And if we had continued to go without the pandemic, if we track the red line to the top, the contribution to global warming by 2050 is predicted to be about 0.1 degrees Celsius, which might sound really small, but it's massive. So that's part of the reason why we need to do it. And then the other lines are kind of showing what would be the targets that we want to set. And so the target based on the Paris Agreement to be set is that we have a long-term decline of minus 2.5% per year after 2020. What has the European Union done to mandate this? They've set minimums for the amount of SAF that needs to be provided at European airports. And this means that every airport across the EU, by different periods of time, need to be fueling aircrafts with a fuel that's blended with a certain blend percentage of SAF. So the targets, at least in the short term, are 2% SAF by 2025, 6% SAF by 2030, 20% SAF by 2035, and 70% SAF by 2050. And a subset of that blend percentage is also a power to liquid type fuel, which is a fully synthetic fuel, which I'll describe a little bit briefly on another slide. Yeah, and those requirements will apply for any flight leaving the EU, independent of where it's landing. So that's a bit of the background on why exactly we need to do this and why Rolls-Royce has supported this initiative so much. There was then the net zero report that was published. So this was published in 2021. And this report describes on how our company will be able to hit net zero by 2050. It's quite a massive report. It's publicly available, very interesting stuff. But from a SAF perspective, there was a major target that by the end of 2023, we will have tested all of our in-production engines on 100% SAF, which for business aviation was the 710, the 725, the Pearl 15, and the Pearl 700, which we achieved by the end of last year. So we've hit that target. And I'll discuss a little bit about the results of those tests later on. Sorry. Okay. So that's the background. And then what is the overall strategy for, this is not just a purely Rolls-Royce strategy, this is like an overall strategy. And I think one thing that's really important to say about sustainability and about SAF is that this is not about Rolls-Royce and what can Rolls-Royce do, that's part of it, but this needs to be an industry-wide collaboration. We can't do this alone. We need to have support from the government, we need to have support from our airframers, we need to have support from other engine manufacturers. So the journey to sustainability is going to be very, very difficult. It's not an easy problem to solve. And I think the boundaries of our company has a huge amount of influence, and we need to be working together with the other companies in our realm to really be making a difference. So overall, the journey to net zero, there's many different ways to look at it, and we need to pursue multiple solutions. So the first one is obviously burning less fuel. So if we make highly efficient engines and then aircrafts that reduce the amount of fuel that's burned, that's a really, really significant part of getting to net zero, because the less fuel you burn, the less CO2 and other pollutants you'll then produce. If you go to the far right, so these are alternative sources of aviation. So electric and hydrogen, those are considered revolutionary technologies. So those would require a very new certification process. There's a completely new infrastructure that would be required for those. But those will take more time. So that's not something that we could implement. There's also not necessarily solutions for the full range of different flights that based on those types of technologies right now. And the reality is that we have a fleet of many aircrafts that are flying around, and those will continue to fly for another 50 years. And so you need something that, without massive modification or investment, would be able to become less CO2 negative. And that's where SAF comes in. So SAF is really a greener fuel. And these three types of activities need to be really happening in parallel in order for us to hit our net zero targets. And this sort of shows the civil aerospace market and technology landscape until 2050. So there's many different types of flights, and every different type of flight might have different solutions that are relevant to them. So UAMs, for example, there's a more feasible possibility that could be serviced by a battery technology. For slightly longer flights, there's combinations potentially between, a gas turbine hybrid electric solution or a hydrogen solution. Currently, with some of these revolutionary technologies, there isn't a way forward for a long distance flight. And when it says here wide body or narrow body, it's kind of independent on whether it's a civil large aircraft or not, because our business aviation jets travel extremely long range. And there just isn't a battery that exists at this time that could power an aircraft across the ocean. And so those types of flights will very likely continue to need a gas turbine burning something to be able to service. And that's where SAF comes in as a relatively elegant solution. There's a lot of long-term potential for the other types of technologies, but that's going to be, from a certification perspective, much more challenging, and it's still quite new in its development phase. This shows sort of worldwide fuel usage. So the wide body, the long range flights are definitely a smaller amount of the overall operation of aircrafts, but they also consume the most fuel. So that's the thing that needs to be kept in mind also, that even though most aircrafts are servicing like a more of a regional area, they don't consume as much fuel as the ones that are going from Berlin to Montreal, back where I live, for example. And the different types of operations may have different solutions that could be used. So a turboprop solution or that type of range, maybe there is some sort of a form, at least now, that could be serviced by hybrid electric or full battery, etc. But for the moment, in order to reduce the CO2 effects of that 62% of fuel that's being burned, SAF is currently the only feasible solution. Okay, so a little bit more about SAF itself. How is SAF made? So there's currently the different types of SAF that are approved. There's 8 different pathways that have been approved with ASTM, and currently they're all made from bio-waste mass. So what that means is that there's different waste products that could be collected from different industries, and those can then be processed and then used to create a kerosene equivalent fuel. So there are several different types. There's Fischer-Tropsch process, which is basically creating or making fuel out of garbage, carbon garbage. Hydroprocess ester and fatty acids. So those, most of our engine testing has been done on that type of fuel. That fuel is primarily produced by using used cooking oil. So that's a very feasible way of making fuel. Then there's other pathways, which include agricultural wastes, oil, fats, and greases. And then algae is an interesting one, because algae is something that's very quick to grow. It requires like no water, and it can be grown in mass amounts. This pathway is, I haven't actually seen any fuel coming out of it, but because it's still in a relatively small volume, but there's a lot of potential to be able to produce fuel using that type of pathway. And what that means, at least what's been approved now, is what's called a drop-in solution. So a drop-in solution, what that means is that you can blend 50%, up to 50% of your SAF synthetic blend component together with 50% kerosene. It then gets recertified, which means a sample is taken. It's compared against the specification for a fully kerosene fuel. It gets relabeled as Jet A1, and then off it goes. So it could be that the fuel that we're receiving here is up to 50% SAF, but you would never know, because it gets shipped here as Jet A1. So that's what a drop-in SAF solution means, is that in all, from a certification perspective and a property perspective, it's basically kerosene. And there's several of these that are, I'll go into that a little bit later, but there's several of these that are approved up to 50%, some of them up to 10%, depending on the similarity from a properties perspective to kerosene. This is the process that you have to go through to approve a fuel, including a pathway. So the ASTM doesn't approve anything. They're just an approval body. So they sort of like the meat, they're like the PCB, you know, they monitor the process, but they're not the ones that say, yes, this is the solution. The approval is done by the different OEMs, including us. So that's by private industries. So on the different phases of the ASTM process, there's Rolls-Royce, GE, Safran, Boeing, blah, 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 blah. And they all sit there and they're responsible for reading all the reports that are generated after a certain amount of testing. And then they agree, yes, we approve at this phase that the fuel is meeting the requirements or not. It takes years to go through this process. This is not straightforward and a significant amount of testing. But just to give an overview that every single pathway that will get approved has to go through this whole process to be able to show that it's in fact usable in the field. And this process is defined by D4054. That's the approval process specification. The SAF landscape is definitely evolving. So like I mentioned before, there's 8 pathways that are already industry qualified. Some of them were qualified back in the early 90s, which is really interesting because SAF is not new. It's been approved for quite some time. It's just that it's never been promoted that much. And the big reality about SAF is just it's not available. That's the big issue about it. We're hoping that that will improve. And there's a lot of initiatives in place, like the ones I mentioned before by the European mandate, that it will start to increase. But yeah, some of the pathways have been approved since the early 90s. And some of those existing pathways are approved up to 50%. And there's a lot of work ongoing now to demonstrate that you could actually, it would still be considered a blend component, but you could use it up to 100% and it would still get recertified as Jet A1. So it's 100% sustainable. It's not a fossil-based fuel at all, and it would be qualified at 100% to be used on an aircraft. That's ongoing. That's sort of the second item here about 100% drop-in. So what's happened now is that the spec has been approved by the ASTM on what that looks like. And then the work is ongoing now to see how to get that approval for a fully SAF fuel up at 100%. That would be ideal. The thing is that with the specification that defines kerosene, there are optimized properties that are outside that spec that from an environmental perspective could have a significant amount of benefit. For example, the reduction in aromatics inside of a kerosene fuel is a direct contributor to contrail formation. And as we get to the point where we are able to certify a 100% non-drop-in fuel, that's really optimized for environmental impact. And that's by some of the properties inside of the fuel would be outside of a standard kerosene fuel. This is much better for the environment. However, there's a significant amount of additional investment involved to do that. Because you would have to have separate tanks, you'd have to have separate fuel transport systems. So the investment is significant, but the payoff from an environmental perspective is also very significant. And what we did as a team, and a lot of people here were involved, is that we've tested all of our in-production Rolls-Royce civil aero engines. Almost all of those tests were done on a non-drop-in fuel, rather than on a drop-in fuel, with no exceptions. Yeah, no exceptions. So that's that's sort of the next phase is more and more pathways to get in up to 50%, and then eventually also work that would go on to be able to blend 2 SAF fuels together. So currently you can only blend with kerosene, but at some point the intention is to be able to blend Annex A1 with Annex A8, blend that together up to a certain percentage and for that to be approved, but that's not fully through the process yet. These are the famous feedstocks and the blend components that are available. A8 is the last one that just came in, a bit about how they're made and what percentage they're approved up to. So the A4, A6, and A8, these ones have the potential to be able to be used at 100% and still match a drop-in specification. So we haven't done any engine testing on those 3. We did all of our testing with A2. But there's a lot of work ongoing eventually that when those fuels are available at a certain volume that we could look into them more. a little bit more about synthetic blend components. So there's a lot of different companies that are popping up all the time that are coming up with new feedstocks to be able to produce SAF fuel. So maybe some of the ones that are a little bit more well known. So Virent. So anybody who worked on the 725 flight would know about the Virent one. So Virent is in itself it's just a synthetic aromatic, and that was used on the 725 flight tests because the engine didn't require it, but the fuel system supplier from Gulfstream said that they needed to have some level of aromatic due to some concerns about fuel leakage on the aircraft side. So we ended up blending with this Virent component. I mean, a synthetic aromatic component is very powerful because if you blend it with a HEFA fuel, you would get a drop-in fuel. I would imagine in the future, this synthetic aromatic blend component will no longer be relevant because you could get it via some of the other pathways on their own. But that's a company that a few people might be quite familiar with. Phillips 66. So this is a company that's basically taking car tires and then converting them into rubber pellets, and that could be used to make synthetic fuel. And this is one of the fuels that's looking like it has potential to be used in one of the all fossil fuel goes through a processing plant. You can take the same processing plant and inject a sustainable feedstock at the same plant and use the same process and get sustainable fuel out the back. And this is one of the feedstocks that's looking promising to be able to go through that process. On the left, there's some other interesting ones in the pipeline. Firefly is particularly interesting. This is a British company that's looking into making sustainable fuel out of poo. Yeah, there's a lot of carbon that comes out of us and animals. And basically, I mean, all that stuff just sits around and produces methane. And methane is also a greenhouse gas. So if there is some way to be able to take poo and make it into aviation fuel, I think that's a good thing. I wouldn't want to work at that factory, but it's definitely got some opportunities. Yeah, and then several other companies, just to say that there's a lot of work out there to be able to find more novel feedstocks, because the real issue with SAF is that the natural feedstocks are not available. Other than poo, that's quite available. But anyway, yeah, just to say that there's so much work going on in the industry now because the availability of SAF is so small, and being able to develop new novel feedstocks is going to be really, really critical for hitting the targets that the European mandate has set. SAF is not all rosy. There are definitely some challenges that have to do with it. The biggest one is cost. So SAF fuel will cost 2 to 5 times as much as kerosene, at least it does now. A lot of that is going to have to be, that's going to be managed. Does that mean flight prices will increase potentially? How can we manage the cost of the fuel? I think that the more that it's available, the cheaper it will be. The more novel feedstocks that are developed, then that will drive costs down. But at the moment, SAF is significantly more expensive than kerosene is. Certain countries have, actually in the United States, SAF is cheaper than kerosene. The government has put this Inflation Reduction Act, which affects that price. But definitely in Europe, SAF is significantly more expensive than kerosene is. So that's something that needs to be managed. It's also scalability. So right now there's about 6 million barrels of aviation fuel used a day to power aircrafts, which is about 300 million tons per year. And by 2050, considering all increase of the population of the Earth, increase of the population of the middle class, etc., we're going to need about 500 million tons of SAF a year to support aviation. That's a massive number. So there's going to be quite a lot of investment that's going to be made to be able to, let's say 70% of that to be sustainable. So the investment required, I already mentioned that. And then it really needs to come down to policies and investments that are going to be coming, or initiatives that will be coming from the government. But I think that, there's no way we won't be able to minimize global warming from an aviation perspective without SAF. I don't think there's no other elegant solution available right now. And SAF is not the end of the story, but it's a really good bridging technology until new technologies are available. A little bit about, where the different SAF is going to be coming from an industry perspective. So the plant to oil fuel, so this is really HEFA or a HEFA type fuel. So unfortunately, we don't eat enough French fries to be able to fuel every aircraft in the world. But there is, that's really the main SAF fuel that's available right now, the stuff that's made from used cooking oil. But you can see that from what's required to support aviation moving forward, that's not nearly enough. And then there's going to have to be development, which is ongoing at the moment, to use more waste and biosources. So that's stuff like using carbon, garbage, poo, and some other stuff. And then bioethanol to jet is another technology that's also ongoing to be able to cover that gap. And then moving further into the future, there's e-fuels or power to liquid fuel, which is a completely synthetic fuel that doesn't require any bio-based feedstock, which I can describe briefly on the next slide. But yeah, the trajectories are all illustrative, but just to show that there's also, even for SAF, there's not a one-fits-all solution. It's going to need, you know, many different solutions to come together to be able to achieve the overall goal. A bit about power to liquid. So this is power to liquid fuel is basically using power from a sustainable source, so wind or solar, and then taking water to produce hydrogen, and then doing some sort of carbon capture and putting that through a Fischer-Tropsch process, and then creating liquid through hydrocracking. So it's a relatively simple chemical process. Let's see. This type of, there are a few facilities that are already open, but they make very little volume, at least right now. And the real challenge with this type of fuel, at least for the moment, is finding an affordable, sustainable energy source. The thing is that with a good collaboration in different parts of the world where the sun shines, I don't care if the process is efficient or not, because the sun's going to shine anyway. So efficiency is not the target, but being able to get an affordable energy source is a challenge. This would be extremely elegant, because if you could set up these types of facilities right near airports, then you would be able to produce sustainable fuel near an airport. In certain, I mean, with the exception of the month of May in Berlin has been beautiful, but generally it's pretty gray here. It would be very difficult to produce everything based on solar power, but looking at other sustainable energy sources like wind or nuclear, I mean, that would be another option. But yeah, so overall process efficiency, infrastructure, and costs, because these types of facilities don't exist yet, so they would need to get built. You have to keep in mind also that when you put up a new facility, you produce a certain amount of CO2. So it's all about the life cycle. So there's a big challenge about the initial investment, the initial production of CO2, and then making sure that with the fuel that you're using, you're reducing your global warming counteracts the increase that you would have by setting up all this infrastructure. So it's not easy. Yeah, so overall, what are some of the benefits, obviously, of SAF? I've touched on them already. So overall life cycle reduction of CO2. The other thing about SAF fuel, at least the bio-based SAF fuel that we've been using right now, is it has a higher energy density by mass, which is very attractive. If you have an aircraft that's not fuel volume limited, that means that for the same mass, you could fly longer because you carry more energy in the wings of the aircraft. If you have a volume limit, then it kind of works in reverse, because SAF is less dense than kerosene, and you might actually have less energy. But at least for business aviation aircrafts, we tend not to be volume tank limited. So that would be a benefit, to be able to sell additional range on some of our products. And one of the big benefits from an environmental perspective is the reduction of contrail formation. So contrails are as a result of unburned particles inside of a kerosene fuel, which is NBPM. So those particles, when they're come out the back of the engine at certain altitudes and temperatures, they will crystallize and form these contrails. And contrails, particularly when they're over the water, they prevent that when the ocean heats up over the daytime due to sunlight, the heat tries to rise away from the planet and go in the atmosphere, and then because of contrails, it reflects back down and reheats the ocean. So contrails are very bad, potentially even more bad than CO2. It's yeah, that's the question of the day, I guess. But generally not good. There's also an improvement in air quality because of a reduction of smoke and particles, the lower aromatics. So the aromatics, when you go by a gas station. Oh, can someone go on mute, please? When you have a lower amount, so when you go to, sometimes at an airport you can smell fuel. SAF fuel doesn't smell because it smells like water. Don't drink it, not good. But anyway, it's too valuable. We don't have enough against our attrition. And also, sulfur is a byproduct of how fossil fuel is extracted from the earth. And having lower sulfur is also better for air quality. So those are some of the other benefits from SAF. Technical challenges, there are definitely still some. So there's some compatibility issues between an aromatic-free fuel and some of the materials we use in our legacy products. We've had quite a lot of learning over the last years that there's a particular type of rubber that was used in sealing material on legacy aircrafts. That rubber swells under the presence of an aromatic in the fuel. And then if you use a SAF fuel, it doesn't have the same swelling effect, and then you get leakage. Luckily, our more modern products have no nitrile rubber seals in them. We did put a lot of checks on that already, but it's not just the engine and not just the aircraft, it's the whole fuel transport system that needs to be checked. So the lorries, the tanks, what's at the airport, blah, 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 and some of those have been set up eons ago. So that's something important that needs to be checked before putting SAF into the system. Have lower lubricity, so that tends to be the trend on a zero aromatic fuel. So fuel pump wear is something that you need to be looked at. You can add lubricant additives into the fuel, but those are also not good for the environment. So there's got to be endurance testing that would need to be done on a lot of the different mechanical components on the engine before we could approve like I say, a 100% non-drop-in SAF. And then generally the SAF fuel, like I said before, has a lower density, which means that some fuel pump, also endurance testing would need to get done, because if you take a big gulp of, I'm a fuel pump and I take a big gulp of fuel inside, I have less energy by volume than it would if it was kerosene. And if your fuel pump is limited by volume, then you may have a risk that certain flight conditions, you can't pump enough energy into the engine. So that's something that also needs to be thoroughly tested before we could approve a 100% non-drop-in SAF. Okay, I'm going to complete the lecture with a little bit about all the testing that we've done. So us and our friends in Civil Large. So I was involved in almost all of these tests. It was a lot of fun working with really, really great people, also doing cool things. So these are the 4 engines that we've tested. On ground in business aviation. So the Pearl 15 we tested in August of last year. It was a joint venture between the hydrogen team and the SAF team. Cool teams working together. That was successful. The Pearl 700, I think, was the first. Well, it was definitely the first business aviation ground test that was done in 100% SAF. That was also done here in Dallas. The Pearl 10X, that was a really, really good learning point, because that engine was used also where there was back-to-back emissions measurements done on the engine. So doing the emissions runs on kerosene and then repeating those runs on SAF confirmed a lot of our predictions about emissions coming out of the engine on a SAF fuel versus on a kerosene fuel. So a really good learning point, also a good confirmation that our predictive tools are correct. And then the 710 was the last one we did at the end of last year on a HEFA fuel, and that was done in Rolls-Royce Canada. Valuable lessons learned were learned on every one of the tests, and I think the overall conclusion is there are no significant impacts on the performance of the engine running on a 100% SAF fuel versus a 100% kerosene fuel. So that was the takeaway from pretty much all of the tests. On the Civil Large side, so they had to test more engines than we did, but a lot of really good learning points on that one. The UltraFan, I think, is an engine that probably everybody's familiar with. So the UltraFan ran their entire EDP program with the one engine EDP, but they ran that one engine entirely on 100% SAF, which was really, I think, great for such a product. And yeah, so these were all the engine tests that were happening on ground. Very similar conclusions to we had on business aviation. Yeah, so that was then completed all before the end of last year. And then a bit about flight testing. So we did several flight tests. The one that I was involved with, and a few people in the room were also involved with, was on the AR725 on the G650. So that was done at the end of 2022. That was a single engine on 100% SAF. This was the first time we did a blended, this is the first time we did a drop-in SAF. So this was a blend between a synthetic aromatic and a HEFA fuel. It wasn't 100% drop-in. The density was a bit below the spec, but close enough. And we just, single engine, and that was a pretty cool experience, and with really, really good results. And the greatest feedback I think I got from that was from the pilots. So the pilot said, if you hadn't told me there was another fuel in the tank, I would have never known. So the handling of the engine is absolutely not affected by SAF, which is, I think, the best feedback you can get. Other tests that were done on the civil large side, so on the Trent 900, on the A380, this was on the flying test bed. So these were 2 of the engines out of the 4 that performed on SAF. The ECLIP program was also doing in-flight emissions measurements on 100% SAF. 1 engine on SAF, so it confirmed that you have a reduction in particulate matter on the SAF engine that you do have on the kerosene engine. So a lot of really good learning there. And finally, this was a huge accomplishment at the end of last year. So this is a commercial aircraft. So this was a commercial aircraft that flew from London Heathrow to JFK, New York, carrying, so they weren't allowed to call them passengers. They were called observers. But there was 100 observers on the aircraft, including Richard Branson and several of our Rolls-Royce colleagues and a lot of journalists and stuff. And both engines were 100% sustainable fuel on both sides. And the beauty about that flight was that they landed in JFK, then there were like a whole bunch of pictures. Then they disembarked the passengers, they made no modifications, and then new passengers got on, they fueled with kerosene and it flew back to London. Which shows that you don't, that's one of the most important things about SAF, is that not every airport in the world will have it. So you want to be able to land at an airport in some country that doesn't have SAF and still be able to tank. You don't have to fly to an airport that has only SAF, because that would make it not so usable everywhere. And this aircraft is a perfect example of that. That you could land, take the people out, put normal fuel in, and then just keep flying. So great accomplishment in the company. Okay, so that's all I had. I think we have some time now for questions.